Hello everyone and welcome to the second lab of the Organic Chemistry Lab series, and this week we're doing acetanilide. So the purpose of this lab is to synthesize acetanilide, which is this compound right here, that's the molecular structure, and then we're going to purify it by recrystallization, which is a technique used to purify organic solids. And then the second purpose is to evaluate the purity, so figure out how pure this product is, by melting it and figuring out what range of temperatures does it melt at. So a little bit of the importance of this molecule as it pertains to medicinal chemistry, which is the development of drugs and bioactive compounds. Acetanilide is an older molecule discovered in the late 19th and early 20th century, and it was found to be both an antipyretic, which means it reduces fever, and an analgesic, so it relieves pain. So let's discuss a little bit about how it accomplishes that. And in order to discuss that, we're going to have to take a look at something we're going to call the pain pathway. So in your body, you have fats, and these fats are called lipids. And one of the fats that your body makes is called arachidonic acid. It's a 20-carbon amino acid. Now, your body is going to take this compound and convert it into a different compound called prostaglandins. Now, these prostaglandins are responsible for causing inflammation, pain, and fever. And they do so by acting as a messenger, and it basically tells your cells that it needs to produce an inflammatory response, so a headache, muscle ache, and so on and so forth. But this conversion doesn't occur by itself. It needs a little bit of a helper. And to do that, the helper is called cyclooxygenase, and sometimes abbreviated as the COX enzyme. So this compound here is an amino acid. It's a protein, a special type of protein that acts as an enzyme. And an enzyme is a biocatalyst. So a catalyst is a substance which increases the rate of a reaction, but is not transformed by it. And in this case, because it's a protein and it serves that function, it's a biocatalyst or an enzyme. So this pathway occurs and causes pain in our bodies. So if we can figure out a way to deactivate this enzyme, we can somehow reduce pain, inflammation, and fever. And that's what the molecule of acetanilide does, is it basically binds to the cyclooxygenase and prevents it from doing its job. And once it binds to the cyclooxygenase, this reaction no longer occurs. So if this enzyme can't work properly, then arachidonic acid will not be converted into prostaglandins, and you'll have pain relief and lower fever. So that's how all of that occurs. So now let's talk about some of the stoichiometry of this experiment, which is all the math and numbers and measurements that deal with how much of each reactant we're adding. So one thing I wanted to mention is that acetanilide, let me get the structure here, if I can find it, there we go. Acetanilide was actually found to be a toxic molecule. So instead, they figured that this molecule here, with an extra OH group, was actually less toxic, but just as effective. And this molecule, whose common name is acetaminophen, is actually the compound in Tylenol. So Tylenol is the brand name, but acetaminophen is the common name. So for the purpose of this exercise here, we're going to look at synthesizing acetaminophen. So the synthesis will be similar, but for this purpose, we're going to do a little exercise with acetaminophen. So on your worksheets, it's going to be a little different. Instead of synthesizing acetaminophen, it'll be acetanilide, and instead of starting with p-aminophenol on your worksheet, it will say aniline. But the process is the same. So when you do a synthesis in organic chemistry, you have something like this, and it's kind of like a stoichiometry table. And on the left side, it's like a general chemistry reaction. So you have your reactants, p-aminophenol, acetic anhydride, and it's converted into the products. One is acetaminophen and one is acetic acid. So in order to figure out how much of the quantities we're going to get in the end, we have to fill out this table. So we start with 5 grams of p-aminophenol, which is specified by the procedure in our hypothetical example. So if we have 5 grams of p-aminophenol, which I will abbreviate as PAP, we can convert that into moles using the molar mass, which is provided for you. So there are 109.13 grams of p-aminophenol in 1 mole. And the goal here is to get into millimoles. So a millimole is like a milliliter. It's 1,000th of a mole. So in 1 mole, there are 1,000 millimole. And if we input this set into our calculator, we can figure out how many millimoles there are. So 5 divided by 109.13 times 1,000, and we get about 45.8 millimoles of p-aminophenol. So we can write that in here, 45.8. Okay, we can use the same process to figure out the millimoles of acetic anhydride. But the only difference is we're starting with milliliters, because when it was measured in the experiment, it's a volume, not a mass. So 5.33 milliliters of acetic anhydride, which is AA, I'll abbreviate as AA. And now we're going to use the density. So there's 1.08 grams of acetic anhydride for every 1 milliliter. And now we can go from grams into moles, just like before using the molar mass. So there's 102.09 grams of acetic anhydride and 1 mole of acetic anhydride. And just as before, there are 1,000 millimoles in 1 mole. So if we input this set of calculations, we get 56.4 millimoles of acetic anhydride. So we can fill that in right here, 56.4. Now, equivalence is an interesting term because it describes the ratio between the reactants. And normally the limiting reactant, or the reactant which will run out first, and because these react in a 1-to-1 ratio, whichever has less millimoles will be the limiting reactant. So in this case, p-aminophenol is the limiting reactant because it has less millimoles. This describes the ratio between these two values. So if we want to figure out how many equivalents of acetic anhydride we have, we divide this number by this number. So we can take 56.4 millimole of acetic anhydride, and we're going to divide that by 45.8 millimole of p-aminophenol, and we will end up with an equivalent value of 1.23. So that's how many equivalents, 1.23 equivalents of acetic anhydride we have. And that makes sense. There is a greater quantity of acetic anhydride than there is of p-aminophenol. The final calculation that's important here is to figure out the theoretical yield. So in order to figure out the theoretical yield, we take the limiting reagent and we convert it into the product we're looking for, which is acetaminophen, which is what we predict. So we'll start with 45.8 millimoles of p-aminophenol. Now you'll notice because they're in, remember this is a balanced reaction, so there's a coefficient of 1 here, it's just not shown. They react in a 1-to-1 ratio, so if I have 1 millimole of p-aminophenol, I will generate 1 millimole of acetaminophen. So for formality's sake, we can write that in. So 1 millimole of p-aminophenol will give us 1 millimole of acetaminophen, ACM. And then we can go from millimoles into moles. So there are 1,000, there's 1 mole for every 1,000 millimoles. And from moles we can go into grams, and I've written in, and this will be on the same as your worksheet, you'll have the molar mass here, which is 153.17 grams per mole. And this will give us the theoretical yield. So if we plug this into our calculator, 45.8 divided by 1,000 times 153.17. And we get a theoretical yield of 7.02 grams as our theoretical yield. Now, for example, let's assume that our reaction, like we perform this reaction and we get a yield of 6 grams. So to figure out the percent yield, It's getting a little crowded in here, but the percent yield will equal the experimental yield divided by the theoretical yield times 100. So say we get 6 grams of product and we expect 7. We multiply that by 100. Let's figure out what that percent yield would be. So 6 divided by 7.02 times 100, which gives us a yield of 85.5%. Draw a little arrow here. 85.5% as our percent yield. So your worksheet will be a little different. It's going to use a different table because it's not making acetaminophen, but the technique and the process used to make it will be the same. Now let's discuss recrystallization. So we've synthesized our acetanilide, and now we got to figure out how to purify it. So recrystallization is the purification of solids that differ by solubility. So last week we were separating liquids that differ in boiling point. So now we're going to separate compounds based on their solubility. Now the target compound ideally is soluble at high temperatures but insoluble at low temperatures. And you'll see that in the reaction. You'll see that when the reaction goes to completion, you'll have a bunch of solid, white solid. And that's the compound. But there's also some impurities in there. And ideally we want the solvent to dissolve the impurities at both a high and low temperature. So to simulate that, I've got a little interactive exercise here. So we have some of our product here, and this simulates a product mixture. And you can see we do have some impurities. We have some leftover aniline, and we have some acetic anhydride that's also left over. And we need some way to remove those. So if we add some extra water to this mixture, so this is supposed to simulate a beaker, by the way, and then we heat this mixture up, we can dissolve all the compounds so that everything is dissolved. It'll look like a translucent mixture. But once it begins to cool, if we cool it slowly, the acetanilide molecules will join together in a very specific order, and that's what this little jigsaw puzzle is supposed to simulate. And when these molecules aggregate together to form crystals, they will exclude the impurities, so they kind of squeeze the impurities out in order to form a highly ordered lattice, which we call a crystal. So this is simulating that we have our crystal, all the impurities stay dissolved in the water, and now this crystal can be filtered away, and then all of these can be filtered into the filtrate. So we've got our pure crystal, and that's how recrystallization works. And hopefully we'll get some beautiful crystals in the experiment when you see it. So the final thing I wanted to touch on is melting point. So in order to figure out how pure, how well our crystallization went, we have to figure out the melting point of our compound. And melting points are traditionally always recorded as a range of temperatures. So it's a little ironic that there is a melting point, but is recorded as a range of temperatures. The first temperature we record is when the substance begins to melt. So we see some liquid, we record the temperature. Now once all the solid has been melted, we record the second temperature. Now the narrower that range is, ideally you want the range to be no more than perhaps a degree Celsius, the more pure the compound is. But if we have a very wide range, say 5 degrees or more, then our compound is said to be less pure. And in the literature, acetanilide has a melting point of 112 to 115 C. So this is what we're going to be shooting for when we do our recrystallization. So thank you all for watching, and we'll see you in the experimental. Alright, so we're going to begin our acetanilide synthesis here, and we've got our reaction vessel, which is a 125 Erlenmeyer flask. We have 2 grams of aniline, which is a yellow liquid. We have 2.5 milliliters of acetic anhydride. So these are our 2 reactants, and our solvent for this reaction is about 15 milliliters of water. So first we're going to add the 15 milliliters of water to the Erlenmeyer flask. And then we're going to pipette in the aniline. So I'll get a clean pipette, put on the bulb, and we can pipette this in. And you want to make sure you transfer all of it to the vessel. So, And as you can see, the aniline and the water are insoluble, which is why it kind of looks like oil and water. So they're just kind of floating in each other, not really dissolving. Okay, secondly, we'll get a clean pipette, put the bulb on it again, and now we're going to add our acetic anhydride. Now when this occurs, the reaction is very quick. It's a very fantastic reaction because it occurs very quickly and there's very little wait time. So we're just going to add the acetic anhydride slowly, maybe in a few portions. So we'll put in a little bit and then swirl it around a little bit, and you can already see the reaction mixture turning a little turbid. We'll add a little bit more. Swirl it around again. And already you can see the solid happening, but we haven't even added all of the acetic anhydride. So now we're going to add the remainder. And swirl it for a few seconds, and as you can see, the reaction is pretty much complete because all of the liquid reactants are consumed, and now we've got a bunch of solid, which is our crude acetanilide, which we will use in our next step, the recrystallization. So we've got our reaction mixture here, which we've let settle for a few minutes, and for one of the questions on your worksheet, we're going to do a little test here. So I'm going to take this pipette and just get a little bit of the liquid of the reaction mixture. So you can see I've got a little bit of liquid in the pipette, and I'm going to apply some to some pH paper. And if you can see, the pH paper turns a red, and the red indicates that the pH is about 2 to 3. So what in the reaction mixture is causing it to be acidic? So the next step is the recrystallization, and this is really the main emphasis of this week's experiment. So in last week's experiment, we did a separation of organic liquids by their boiling point, so using distillation. This week we're going to use a similar physical separation method that separates not based on boiling point, but instead based on solubility. And that's going to deal with recrystallization. So to compare and contrast what the non-recrystallized product and the crystallized product, how pure they are, we're going to take a small sample of these crystals. So I'm just going to take a spatula and maybe grab some off the edge. Oops, it's a little challenging. Oops. And I'm going to place some in a vial to save for later. You can see we've got a little sample in there. This is the non-recrystallized product. So we're going to compare the melting point of this to the melting point of the recrystallized product, which we're going to make right now. So to do that, we're going to take our entire mixture here and we're going to transfer it to a beaker for recrystallization. So got it, and it's kind of hard to do, but you want to try to get most of the crystals over in the first pass. And you can see that there's still quite a bit of solid adhering to the walls of the Erlenmeyer flask. So we want to transfer all of this over. So to help do that, we're going to use a little bit of water. And swirl it around a little bit. Maybe we'll do it a few more times. See, there's still a little bit right here, so try to shoot it off. And we've got the majority of it, so this stuff we might not be able to get out, and that's okay. That's probably a few milligrams worth, not that much. And to finalize the recrystallization step, we're going to add 50 milliliters of water. So the total volume of water right now is somewhere around, well, since we squirted some for the transfer, the total might be somewhere in between 80 and 100 mils. Yeah, so we've got around 100 milliliters of total water here. But the exact value is not super concerning. You just don't want to have too much. So now that we have that, we can move on to the next step, which is to heat this mixture until all of it dissolves, and then we'll let it cool, and that will form the crystals. Alright, so we've got our solid here in our beaker, which we have not recrystallized, and we're going to begin the recrystallization by placing it on this hot plate here, and we're going to heat it until all of this solid dissolves. And to prevent the water from escaping, we're just going to place a watch glass on top, and we'll see y'all when all the solids have dissolved. Alright, so we've heated our mixture up to boiling, and as you can see, most of the solid is dissolved, but now we've got some oil here. And this is, before it starts boiling too vigorously, I think I will turn off the heat there. That should let it calm down a little bit. But you may have seen, they've kind of been obscured by the bubbles, but there were some droplets of what looked like an oil, and that's something we see a lot with this lab. And we think it's maybe the solid that starts to melt actually in the water. But it shouldn't affect the recrystallization too badly. So now that everything is dissolved, we've turned off the heat, and now we're going to let the mixture cool very slowly, because we want it to cool slowly so that the crystals form very slowly, and they will form nice and big crystals. In general, the bigger the crystals are, and the more slowly you form them, the purer they will be. Alright, so we've taken off the beaker from the hot plate, and we've just placed it on this stack of cork rings. I don't know if you can see it below here, just to let it cool very slowly. So we don't want to chill it, we don't want to put it in the fridge, we just want the crystals to form naturally and slowly. So please enjoy the next time lapse of the crystal formation. I think you will find it very beautiful. So we've got our crystals from the recrystallization, and we're going to collect the crystals using vacuum filtration, which is this apparatus right here. And so the apparatus consists of a Buchner funnel right here, and this sits in this little flask with a sealing ring here, and this flask is hooked up to a vacuum, so it'll speed up the filtration as compared to using just gravity. So the first step is we take our filter paper here, put it on the filter, and we're going to spray it with a little bit of water just to ensure that it sticks. And I'm going to turn on the vacuum just to make sure it's adhered, and you can see how quickly it sucked up all the water. So now we'll take our beaker here, and I'm going to try to get it all into the filter while the vacuum is running. So let's try. Okay, you can see that we got most of the crystals, but there's still a little bit on the side, so we can wash it down. But now you can see the crystals are very nice, very shiny, and rather large. They're much larger than the solid that was in the reaction mixture before we recrystallized it. So let's add a little more water to our flask here. Oops, spilled a little bit. And we'll turn on the vacuum and do the same thing. And as you can see, we got most of it. This stuff on the wall will be very difficult to get off, so we're just going to go with that. And the final step is we've got our crystals on the filter, and we just want to make sure that all the impurities are sucked off and into the filtrate. So we've got a little bit of cold water, and we use cold water here to make sure we don't dissolve too much of our product. And we're going to do the same thing. So as the vacuum is running, we're just going to pour a little bit of this into it. So now that the crystals are on the filter, there's still quite a bit of water in this filter right here, especially on the paper. So what we can do is leave the vacuum on for a few minutes, and the stream of air that's being sucked through the crystals will dry it out a little bit. And we'll let that go for a few minutes. Okay, so we've got our crystals. They've been drying on the vacuum filter for a few minutes now. And now we need to scrape them out. And that's kind of challenging to do. So what I'm going to do is I'm going to do my best to scrape them and put them onto this filter paper here, which will help me get it into the final vial where it's going to be dried. So let's see if I can do this. It's kind of difficult in front of the camera, but you can see these nice fluffy crystals. They're much larger than the solid from the reaction mixture, which tells us that they should be fairly pure and hopefully in a high yield too. So we'll try to just empty them without spilling onto the filter paper. And you can spend a lot of time trying to get every little crystal. Alright, so the battery on the camera died, but you didn't really miss anything. We basically just scraped all the crystals out of the filter, and you can see I've done a fairly good job. You can't always get all of it. There's always going to be some residual on the filter paper. And we've transferred the majority of it onto this larger filter paper, and doing this will help us get it into this cute little scintillation vial here. Okay, so with any luck, and it's very difficult to do this without spilling it, let alone on camera. So you fold in a little taco here and try to kind of nudge it into there. So yep, you can see it's getting in there. Oh, I spilled, so that's alright. It's not too much. In fact, I might just lay that down, and try to use a spatula to kind of break up the crystals because they're so large and they're very difficult to get into the vial. So let's try that now. Okay, as you can see, oh, there's a big crystal, so this is a clean surface, so you can do this. You can kind of take your spill and transfer it into the vial. And there's always going to be a little bit. Students always spill a little bit. It's kind of inevitable, but the amount you spill is so negligible. The majority of it is in here, which is what we want. Now, before we can get the mass on this, so this is the mass of the vial. But before we can weigh it again and figure out how much acetanilide we have to dry it because there is quite a bit of water in here. So in order to dry it, we need to place this this vial into a vacuum desiccator. And the vacuum desiccator is basically a sealed chamber under vacuum and has a little bit of a desiccant in it. So that desiccant will absorb the water from this solid and dry it out. And once this is dry, we can get a yield on it, so we can figure out the percent yield, and we'll let you know what that mass is. And after we can get the mass, we can also figure out the melting point. And it also needs to be dry for the melting point. If there's water, the melting point will not be accurate. Alright, so we've got our purified compound, which has been in the vacuum desiccator and is nice and dry. You can see the crystals are nice and separate. There's no water in here. And the amount of solid in here equals 1.56 grams. So that's the amount of product that we got from this reaction, which you can use to calculate the percent yield. So this is our pure product, and if you'll remember earlier in the experiment, we took a small sample of some of the solid from the reaction before crystallization, and this is what we're going to use to prepare the melting point samples. So a melting point sample is prepared by sandwiching a little bit of the solid in between these little cover slides. And they're little glass lightweight slides, and you don't need much solid, just a little bit. And they're very difficult to separate. So let's start with our purified compound. So I've got my spatula here. I'm just going to take perhaps 1 or 2, you really don't need that much. That looks about right, and we'll place it onto the slide. Okay, I'll try to get them fairly centered. Okay, that looks pretty good. Put the cap back on that, and then we'll take our top slide, kind of sandwich them together. And this is what we're going to use. So this is the first sample. Oops. See if I can get her off the bench here. Okay. You can see they're sandwiched together, and then you place these two onto the stage of the melting point apparatus. And the melting point apparatus consists of basically this thermometer here, which allows you to know what temperature it begins melting at. You have the stage here, which has a heating element, and then you have a magnifying glass here, which you can look through. And when the unit is switched on, there's a little bit of a light, which helps you see the crystals inside of it. And this knob controls the temperature right here. So you increase the temperature, and the trick here is to do it very slowly, because you can easily overshoot the temperature. So I'm not very good at it, but some people are, and they can get it very close to the melting point. So that's how we prepare the sample, and I'll do the same thing for this crude sample. I just won't show it. So the next shot will be of us looking at the crystals through the magnifying glass. Alright, so we're at 111 degrees right now. It's taken a very long time, like maybe 10 or 15 minutes to get here, but it's slowly increasing, and we're almost at 112. And hopefully, with any luck, the solid will begin to melt. Oh! It's melting! At 115. Oh, and all of it is melted.
Did it melt all just...
Yep.
Okay, so,
pretty much.
That actually is a sign of purity.
Yep, very narrow.
Yeah.
Yep. So basically 115 to 116.